Okay, so our notes today are going to begin our new chapter, chapter 12, which is on something called stoichiometry. And stoichiometry kind of has an intimidating sounding name, but it's something that you have been practicing for really forever. So I know you don't have these pictures in your chapter 12 notes packets, and that's fine. I always start this chapter by just putting up some pictures of some recipes here, because that's what stoichiometry is. It's really just looking at recipes and trying to figure out how much product or how much of that particular item you can make based upon what you have on hand. So you can see that like the recipe for 2 ham and cheese sandwiches here is 4 slices of bread, 4 slices of ham, and 2 slices of cheese. So if I want to make 2 ham and cheese sandwiches, I know that that's what I'm going to need. And here's another recipe for another type of sandwich. Each sandwich needs to have 2 slices of bread, 3 pieces of lunch meat, and 1 slice of cheese. So think of that as in like a balanced chemical reaction. Those are your reactants. And your product is going to be 1 sandwich. Right? So if we are given this amount of starting material, this isn't necessarily a balanced chemical equation. This is, what am I starting with? If I start with 6 slices of bread, 12 pieces of lunch meat, and 5 slices of cheese, I can actually only make 3 sandwiches. Why? Because the number of pieces of bread, the 6 slices of bread, will limit, that's why it's called the limiting reactant. It will limit the amount of sandwiches that I can make, right? If I were to use up all 6 slices of bread and had unlimited other ingredients, I would be able to make a maximum of 3 sandwiches, 12 pieces of lunch meat. Well, if one sandwich uses 3 pieces, 12 pieces will only give me 4 sandwiches, assuming I have enough of everything else. And if a sandwich needs 1 slice of cheese, if I have 5 slices of cheese, I could make a maximum of 5 sandwiches. And of these 3 numbers, what's the smallest one? 3. I think if I was doing an assembly line, right, I would stop after I had 3 sandwiches because I would run out of bread. These would be what we have in excess. I would have more than enough of the lunch meat and the cheese. And that's the basic idea of stoichiometry. So we are going to, of course, not be doing this with sandwiches and recipes. We're going to be doing these with balanced chemical equations and ionic and molecular compounds. So if you turn to your chapter 12 notes packet, so some of you guys grabbed them on our last day of school in March, or you can print it out on Schoology. This is where chapter 12 starts. And so chapter 12, stoichiometry. And what we're doing on this page really is just looking at this graphic here. This graphic is showing us what we're going to use as our recipe for the rest of the chapter, which are balanced chemical equations. So here we have, this is the synthesis of ammonia, right? This is 1 molecule of nitrogen gas. Remember, nitrogen's diatomic. 1 molecule of nitrogen gas reacts with 3 molecules of hydrogen gas and makes 2 molecules of NH3 or ammonia. And all these different lines here are just different ways of showing or expressing that same information. We could count them in terms of atoms. We can count them in terms of molecules. And then this is just showing, hey, if 1 molecule needs 3 molecules of hydrogen, then can't we just say that 10, if I multiply everything by 10? And then this is saying, well, what if we multiplied it by Avogadro's number? 6.02 times 10 to the 23rd. And that's where we get this kind of line right here. And this is going to be the one that we use the most. Looking at a balanced chemical equation in terms of moles. That actually 1 mole of nitrogen gas will react with 3 moles of hydrogen gas to produce 2 moles of NH3. These last 2 sentences, or last 2 lines right here, just show us that the conservation of mass is true, that if we convert all of those moles to grams, like we did in chapter 10 a whole bunch, that the mass of the reactants would equal the mass of the products. And then the last line is just showing that, yep, these are all gases at room temperature, that if we converted them all to liters of a gas at STP, we would see that actually volume is not conserved, that we would start with a much larger volume of gas than we end with. So that's kind of yes, a balanced chemical equation, and this is, again, the most important kind of sentence there, that we can interpret a balanced chemical equation in terms of moles. Okay, so now we're going to actually start doing some problems with these. And if at any time you get confused or you're like, what did she say? Just pause the recording and go back. You can do that as much as you want. It's sort of even better than being in class, because if you don't hear something or you don't understand it, instead of, asking, can you go over that again? You could just rewind a little bit and then play it again. So we're going to start doing a whole bunch of problems with these. And the problems that we're going to solve are going to be sort of similar to those sandwich questions from the beginning. If I have 6 slices of bread, how many sandwiches can I make? But now what we're doing is we're working with balanced chemical equations and we're working with chemicals. So today's lesson is going to be on these particular type of problems, mole to mole problems. And so what does that mean? It means I'm going to give you a number of moles. So instead of 6 slices of bread, I'm going to be, like in this one, 5 moles of potassium. And instead of saying how many sandwiches, I'm going to be asking how many moles. When we do these problems, you're always going to be just using one parenthesis. This is just like dimensional analysis. And we use the coefficients from the balanced chemical equation as my conversion factor. So see how this says 2K solid? We kind of interpret that as meaning 2 moles of potassium will react with or is equal to 2 moles of water to produce 2 moles of KOH, potassium hydroxide, and 1, because there's really a 1 coefficient in front of hydrogen, 1 mole of hydrogen. So these are what I'm going to use in my parentheses. And I'm going to use the same rules that we have used for dimensional analysis before. Whatever we're converting to goes on top. So question number 1, how many moles of hydrogen can be produced from 5 moles of potassium? So circle the do, underline the clue. I did that here. And I take the clue, 5 moles of potassium, and I write that out front, and I make a parenthesis. And what goes inside my parenthesis? Well, I'm using 2 clues to help us out here. Whatever is, 5 moles of potassium, that label, that unit has to go on the bottom. So where do I get the numbers for that? That's where I use the coefficients from the balanced chemical equation. So on the bottom, I put 2 moles of potassium, and then, whatever I'm converting to is going to go on top. Well, I want to go 2 moles of hydrogen gas, so I put 1 mole of hydrogen gas on the top. Same rules of dimensional analysis, multiply by the top, divide by the bottom. So 5 times 1 divided by 2, 2.5 moles of hydrogen gas, because of course these units are going to cancel. I didn't really worry about significant figures here, but we will worry about significant figures in all the other problems. Again, this is a show me. So in the folder on Schoology, you will see that there's a document with all the show me's for this. So if you want another video of me going through that problem, you can look that up. Question number 2. How many moles of water are needed to produce 84.6 moles of hydrogen gas? Circle the do. The question's asking me about moles of water. Underline the clue. That's the data that's given to me to start with. So that's the number, 84.6 moles of hydrogen gas. I put that up front, right? That's why I wanted us to get used to writing in our chemicals in the last chapter, in chapter 10, because in this one, we're going to do a lot of switching between one chemical and another chemical. So same thing that we did before, we're using the coefficients from the balanced chemical equation to use as my conversion factors. So whatever unit is out front needs to match the unit down bottom. So the coefficient of hydrogen is 1, so 1 mole of hydrogen. And the coefficient in front of water is 2, so 2 moles of H2O. Multiply by the top, divide by the bottom, I get 169.2 moles of water. And now let's start worrying about significant figures. So this number was a measured number. It has 3. Those coefficients from the balanced chemical equation, they were not measured. Those are exact numbers because remember, they go back to 1 molecule of hydrogen gas will be produced from 2 molecules of water. Since I can't have 1.5 or 2.3 molecules, these are whole numbers, so they're just not going to factor into our significant figure conversations. So my answer needs to have just 3 significant figures, so that's just 169 moles of water. And there's another method for doing these problems. It's called using a Bca chart. The Bca stands for before, change, and after. And this is going to become a real easy way or just another way of doing these type of problems when they get more complex. Right now, it seems like it's more work than the other way. And so on your homework tonight, you're going to have 3 of these that you can that you're going to do, and you can do them using a Bca chart or using them just the same way that we did in numbers 1 and 2. It's totally up to you. When we get more complicated problems, and especially in AP chemistry, you'll see why Bca charts are really useful. But right now, we're just going to introduce it with these one-step mole-to-mole problems. So question number 3 says, how many moles of hydrogen can be formed from, so that's my circle to do, 1.54 moles of water. So this is my clue. So before the reaction starts, I have 1.54 moles of water. The question, does it even ask about potassium or potassium hydroxide? No, it doesn't. So I don't even care about these because the question just doesn't even ask about them. It's asking how many moles of hydrogen can be formed. So we're sort of assuming that at the beginning, we have no moles of hydrogen. So the change is how much does it go down by? And this is really getting you to understand what is going on. What is going on is that 1.54 moles of water are going to react. And at the end of the reaction, I'm going to have no more water left. Because what will have happened is they will have changed into hydrogen gas. How do I know how much hydrogen gas will have been made? It tells me right there. In order to use that change column, I need to use a mole over mole parenthesis, right? So I take my 1.54 moles of water, and using the coefficients from the balanced chemical equation, 1 mole of hydrogen gas will be made from 2 moles of water. And so what does that equal? 0.77. So that means this guy will go up by 0.77 moles. And at the end, I will have 0.77 moles of water. And that's how you could use a Bca chart in order to do a stoichiometry problem. It sometimes helps us to really understand that I will use up all of one reactant, and the product at the beginning I had none, and now I have some. So either use the technique just straight dimensional analysis like in numbers 1 and 2, or like in number 3, a Bca chart to do, and you're doing numbers 1 through 3 in the homework packet, in that chapter 12 homework packet. On Schoology, I'll put the answers so you can check your work. And then on Thursday or Friday's Q&A, I'll answer questions that you may have about 1 through 3. And also later on this week, I will post another video where we go over pages 4, 5, and 6. So the next 3 pages down here, pages 4, 5, and 6, and then you'll have some more homework problems to go over from that. So again, rewind this video if you need to. Try homework problems 1 through 3, and then Thursday or Friday during our scheduled Q&A, ask me any questions that you have. Hope you have a good beginning of your week. It's a beautiful day outside, and I'll talk to you soon.